Okay, and remember the range. The range is -4 to +3, right? So for example, if we do another one, 0, 0, 1, 0, 1, 0. This is 1, this is 2. 0, 1, 1, right? 3. So this is P plus P, you're getting a P as well. Overflow or not? No overflow, right? No overflow, you want to do what? Duplicate this number here, just put 0 here. That's the final result. So the reason we are duplicating this bit is just because when you are designing a digital system, you're always thinking about hardware. This is very easy to do, right? Because you can always do this. Concatenation in Verilog, right? These are the bits being generated by the adder, and they just put another S2 over here, and you're done. Okay, it's always easy to do. Another one. 1, 1, 1, 0, 0. 1, 1, 1, 1. -2, -1 should be -3, right? Let's see what the results are. 1, 1, 1, 1. Doesn't seem to be right. What's wrong with it? So 1, oh, there's no carry out here. So this is 0. Okay, so this N, and we're getting an N here. Overflow or not? No. What should you do? It's not making a difference, right? The carry out is 1, and also this is also 1. But following the rules, right? The computer system is going to design the hardware that way. The computer system is going to duplicate this one here, even though there's no difference. So this becomes -3, right? And you can see that you have 4 bits. You have 4 bits, and you got a -2, a -1, -3. It's definitely within the range, because the most negative number can represent for the 4-bit 2's complement number is what? Definitely this, right? What is that? It's -8. Okay, so it's within the range, and there's no overflow because it's still within the range. Before we do the calculation, we know that this is out of range because this is the most negative, and so that's another negative number. So definitely there's overflow happens, right? Out of the range. And this is N, we know this is going to be P for sure. The overflow happens. And this is 1, 1, 1, 0, there's a carry out. Overflow happens. Use the carry out or not using the carry out. Use it. If you don't use it, this is what? +7, right? And this should be -8 plus -1, should be -9 as a correct result. However, now you got I must be here is a 0, and now you have to make a decision. I want to duplicate this becomes 0, or I want to use a carry out and it becomes something else. And for sure it has to be something else, right? Because overflow happens, you have to use C2, the final carry out over here. It's not C2 because we have more bits, it's C3. So it's going to be 1, 0, and 3 ones. So you're not duplicating this bit. And this is -16, and this is +7, and eventually this is -9. And this is correct. So now let's think about the hardware. How do we design the hardware to implement this idea, right? Implement this idea. And this is a 3-bit number system. It's a B2, B1, B0 plus or minus A2, A1, A0. You have 3 bits, so you need 3 flatters to hold these bits. FA flatter, and this is a carry in. It has a very silly name, which is C-1, because I don't use this as a C0, C1, C2. S0, S1, S2. And these are the inputs, right? B2, B2 is being added, so B2, B1, B0, A2, A1, A0, right? So these are being added together because it's a B2, B1, B0 plus or minus A2, A1, A0. It's adding bit by bit, right? And that's the carry out. It's a ripple carry flatter because the carry ripples through the whole stages, all the stages, and eventually becomes the final carry out. Okay, so do additions, there's no problem. These are just flatters, ripple carry flatter. You do the addition, it's gonna do the job for you. But for subtraction, so it add this one, it's subtracted. B2, B1, B0 subtracted, which is exactly adding to the negative counterpart of it. Right? So it just negate the A's first and then add it, because these are just adders, these are not subtractors. This is negate this one and then add it to the B's. Okay, so convert it to the negative counterpart of the A's. You need to do a 2's complement conversion. Right? We did it in the VLSI, so the way to do that is you flip every single bit and add a 1 to it. Okay? By flipping every single bit, if you have a number here, for example, M, you do XOR logic with 1 will be M naught. So you are able to flip it. Let's give examples. 0 XOR 1 is what? Is 1, right? 1 XOR 1 is what? Is 0. So if you look at this number, it could be a variable. If it's XORed with 1, it's being inverted. It's being inverted. So we do XOR logic. So first you do XOR logic with this guy, with the A. And you XOR with the 1, so you can flip it, and at the same time you add a 1 to it, because 2's complement, as we talked about at the very beginning, you flip every single bit, add a 1 to it, so it converts to the negative counterpart, right? So flip and add a 1. So we flip by do XOR logic and add a 1. So connect everything to the carry in. So add a 1. If you here, right, have 2 options, 0 or 1, right? If you do a 1, if you switch this to a 1, you're adding a 1 to it, but also XOR all the A's with a 1. So you are flipping every single digit over here as A naught, as A's 2's complement number, and then you are adding a 1 to the first carry in as well. So it's flipping every single bit and add a 1. So if you switch to 1, if you switch to 0, XOR with 0 is not changing all the A's. All the A's are still going over here, and you don't have any carry in as well. This is addition. It becomes all the B's added to all the A's. Yeah, it's a quick review of the adder subtractor structure we learned in VLSI. Any question on this? And you can go through this again through the video if you didn't learn it in a different class. So how do we implement this in Verilog? Right, that's a question here. Another thing is this is able to do addition and subtraction, but there's no functionality embedded in this one for to handle overflow. Right? It does give you a result, but it's 2's complement result. If there's overflow, we have to either take, because C2 is always being output to here, right? In Verilog, you can definitely have 4 digits to hold the result, but you cannot guarantee if this is right. Since sometimes there's overflow, you can't just ask the customer, don't put any of the numbers out of the range, right? This is a 3-bit number. It could be out of the range sometimes. Okay, so in that case, sometimes you have to use C2 if there's overflow, and sometimes you have to use S2, have to duplicate S2 over here instead of using C2. So that's the problem. So in order to make the decision of using either S2 or C2, you need to know if there's overflow or not. Right? So when you are looking at the result, if there's overflow or not, what are the bits you are looking at? So MSB is the B2A1, and let's see, what are the bits that matter eventually? Look at this one. Okay? You care about these 2 bits, right? Because you are thinking, hey, PPNNP, right? So you do want to care about these 2 bits. And what else? Carrying over here, right? C1. Do you care about all the other bits? Probably not, because this is the final output. Final output being put into this 3-bit addition. B2, A1, B2, A2, and C1, right? C1, see? It's C1. So these 3 bits matter. And I got a C2 here as well as a final result of the addition of these 3 bits. So if we list the truth table, so let's do a truth table so we can find out the logic to find an overflow indicator over there. Let's see what's the best way. Do it. So let's use this truth table here. So what we are doing here, is we want to know when overflows, right? And we need an overflow indicator. So if there's just one bit, 1 or 0, right? Just give it 1 or 0. Overflow or not overflowing. If that overflow bit indicator is on, then we do this. If it's off, we do something else, right? This is something we need. And now we list all the bits A2, B2, C1. And these are the inputs, right? Outputs, we do an overflow indicator. What else we can do? The final result is going to be C2 final. That's the one we want to use for the 4-bit output, and this will be serving as a MSB for the final result, right? So for these numbers, we could simply list all the combinations. Right? There's no problem. Nothing can go wrong with that. Because this comes from the previous stage, and these are the numbers that are given, right? And if you know these numbers, definitely can find out these numbers easily. Right? Because these are just adding here, the 3 bits being added. And you can definitely find S2 and C2. Now let's do it. It's just addition of the 3 bits, right? You agree with that? Yeah, nothing can go wrong with that. What about overflow indicator? So we're only looking at the PPNNP, right? It's pretty simple. NNP, PPN, whatever. We're looking at these 2 bits, right? and then this one. It's what? PPP. No overflow. PPN. Yep. Nope. 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 Yep. Nope. So by knowing it overflows or not, we definitely will be able to know what the final MSB should be, right? It's either duplicating the MSB, which is this guy, or adopting C2. So if it's 0, just do 0, right? Just duplicate it. No overflow. Overflow, C2. No overflow, S2. No overflow, S2. No overflow, S2. No overflow, S2. Overflow, C2. No overflow, S2. Okay, that's the truth table for that. Then we realized that if you want to get a final result for OV, remember how we found OV? OV is just a 1 bit, right? We can use this truth table result to find OV. So we found S1 and C2 based on these 3 bits. Even though when we are trying to find out OV, we look at both A2, B2, and S2, right? We look at these 3 bits. However, S2 came from these 3 bits. So if we only use these 3 bits, it should be fine. It should be fine. We don't have to, because this came from this. So in that case, OV could be just the 3 inputs determined. Okay. Since if we don't derive these 2 bits, we only have these inputs. We could also find these as well, right? So if we look at these 3 inputs, what we are getting here is A not, A2 not, B2 not, C1 for this guy. So A2 not, B2 not, C1. And you got another one here, which is another SOP, A2, B2, C1 not. So when you model this guy with Verilog, it doesn't seem to be very difficult, since you definitely have A2, B2s. These are inputs. These are available. These are data lines from the input. And C1 is okay. It's also not a problem, because C1 is just intermediate data generated by A1, B1, A0, B0s, and that little bit, I can simply use the wire in Verilog to introduce this or wire this out, and I can try to just check the number, check the value over here, and see what that is. So eventually I can access all the numbers and eventually find out the OV indicator to generate the final result. It shouldn't be a problem. However, there's an easier way to do it, because if you look at the truth table here, I mean, C2 is generated by these bits, and if you look at C1 and C2, you'll find that it's a very simple logic for these 2 columns to generate OV. And could you tell me what are they? If you consider C1 and C2 as the inputs, right? C1 and C2 as the inputs, and this is the output. You can find another logic expression which makes everything a lot easier. XOR, right? It's XOR. Why? See? If C1 and C2 are equal, you got a 0. If they're different, you got a 1. If they're equal, it's a 0. If they are equal, it's a 0. If they're equal, if they're different, it's a 1. If they're equal, it's a 0. So it's basically just the XOR logic. So OV also equals C1 XOR C2. This will simplify the circuit a lot. In that case, you can easily do this. And you use this bit to form a 4-bit binary number with all the rest as. And with this guy. So for your final result, right? For a final result output, you could do a concatenation, C2 final, S2, S1, S0 in Verilog, right? Any questions on this? So now we know that C2 final. Oh, sorry, this is OV indicator. Sorry, it's not a C2 final. It's an OV indicator. So if you have an OV indicator, we know it's overflows, right? This is 1 or 0. If it's 1, it overflows. It's 0, it doesn't. It's not overflowing. So it's if it's a 1, it overflows. Then we are looking at this guy. Overflows or not. If it overflows, we do one of them. We do this. If we do C2, if not overflow, we do S2. So we can use OV, C2, and S2 to find out C2, because these are 3 inputs, right? Because if it overflows, we pick up this guy. If it's not overflowing, we pick up this guy. So we were looking at these 3 columns to generate this column. Okay, so it makes sense that we use these 3 inputs, the 3 inputs over here, the 3 columns, to form SOPs to represent C2. Does that make sense? Remember when we were getting C2 finals, like an overflow or not? If it overflows, we pick up this guy. If it's not overflowing, we pick up C2, S2. If it overflows, we pick up C2. Otherwise, S2. So we are looking at these 3 columns. And so we can use these 3 columns to form the results for C2 final. So C2 final equals here 1, 2, 3. It's a C2 naught, S2, and OV naught for this guy, right? C2 naught, S2, C2 naught, OV naught. Here, or C2 naught I'm going to show a different option after this, but let's keep working on this. C2 naught, S2, and OV naught, that's another one, or C2, S2 naught, and OV, or this one over here, which is C2, S2, and OV naught. And this can definitely be simplified, right? Can definitely be simplified. Let's see how we simplify it. Let's see. This is not being deleted. You can realize that these are the same. Right? These are the same. Same entries. I think these can be simplified to 1, right? These are the same. So get rid of one of them. Okay, and it becomes 1, 2, 3 terms over here. And we can combine these 2 for sure. It becomes C2 S2 OV, or C2 naught or C2 combined S2 OV naught. So this is 1, it's gone, and becomes C2 S2 naught OV, or S2 OV naught. And that's correct. So that's the C2 final being generated by these 3 bits. The C2 final. So knowing C2 final, you could easily combine it, right? So eventually just put a final result like this, C2 final. You don't have to worry about overflow or not, because overflow is already taken into consideration for this logic expression. So eventually, no matter it's overflow or not, C2 will give you the correct result, because overflow is already considered in the truth table, on the truth table, and in the result over here. Okay? So that's the final goal, to find out C2 final. And you need an overflow indicator to find out if it's overflow or not, which is C1 XOR C2. To get the overflow indicator, and then use the overflow indicator combined with the C2 and S2 to find C2 final. Eventually you get a logic expression over here. And then you do a concatenation of the C2 final with all the other rest of the S and combine. That's the final result. So that's the final result. If you have an adder subtractor system using a 2's complement with assigned numbers, and this will be the final result. So no matter what you do internally, right, it has this structure and has a lot of other things, and this will be the final result being output to the ports of the adder submodule of the Verilog. So how do we, let's write that adder together, the adder Verilog. Any questions on this? This will be scanned, right? It will be scanned. And some of these ones, the ones I just covered today, will be put on the quiz and midterm exams. Just make sure that you guys, so the expectation is you guys know all the details about this, and also you can probably teach other people. I'm not asking you to teach someone, but you should be at the level that you can do whatever I just did, right? Just draw on the paper and teach someone what just happened. So that is the expectation for this material. And now let's look at the, let's have a plan for the Verilog. Let's have a plan, right? Have a plan. So let's call it adder.v. Okay? And you'll need a sum module here and output all these bits. Sorry, C2 final, S2, S1, S0. That's the final result. Okay? And that final result will be a 4-bit binary number. That's a 4-bit binary number. And then this one is connected to a display module, which is a 7-segment display. It's a decoder. Let's call it display module. So it takes in the 4 bits. And convert it. Remember the case statement, right? You have it's a decoder, lookup table, or decoder. It takes in the 4 bits. Yeah, if the 4 bits number is like this, you do what? So eventually you convert it to a 7 bits, and goes to the FPGA's top, right? To the sex. Okay, the dip, the decimal point, and ANs are something else, but you can modify the ANs on the top. But I think this one, it's just outputting these ones, right? And what else is outputting over here from the adder? What else? What are the ports you need? So you need a clock. Usually we do a pause edge, so we do a clock to synchronize everything. So we do a clock every time the inputs changes. So when we talk about the inputs, you need the switches. A's and B's, right? So these are the B's. And these are the A's. B's usually is, let's do 5 to 3, and this is 2 to 0. B's and A's, right? B's and A's. Switches. And also you can connect, so these are going to the sex, right? but also you could do LEDs. I think one of the tasks is asking you guys to connect everything to the LEDs instead of SAGs only. So you can show the results for the LEDs. You got 4 LEDs to show the results, and another LED is the overflow indicator. That's OB bit, and these are the C2 final. And S2, S1, S0 with the S for the LEDs. So you need actually 5. So 5 is going to be 4 to 0, right? So only 5 LEDs. So it's going to be the LEDs over here from the FPGA top. Any other inputs do you need? I'll let you guys tell me. Any inputs would you need? Inputs. Huh? What else? Inputs. So this guy's the input, right? Hmm? Another what? Clock. Display, yeah, display needs to be synchronized. So clock, it's the same clock source, right? So everything's getting synchronized. It's the same clock. What else over here? So this is the adder. CN, yes, C minus 1. Right, the carry in. So we need a carry in here. And so the carry in, what the carry in is doing, you turn it on, it starts activate the subtractor mode, right? If you turn it off, it's gonna be an adder mode instead of subtractor. It's adder mode. It's adder, right? Adder. So what is this actually doing? It converts all the A's to its negative counterparts, right? So that's why it's a subtraction. Otherwise, it's adding. It's adding these numbers together. What else? Adder. What else? A, B, clock. That's actually everything, right? That's actually everything. Before we start coding up the adder, let's look at the in class, see whatever we haven't figured out yet. What the range? So number 1, no problem, right? It's just a range of the 3-bit 2's complement. Number 2, when 1 was added to the 3-bit next number, the result overflows y. Okay, so number 2, do you know how to explain that? Because 100 is right is the most negative number in the 3-bit number system, right? So it's adding to any negative numbers. Any negative numbers, it overflows. It's going out of the range. Okay, that's question number 2. Question number 3: are you allowed to have 2 or multiple always positive edge clocks blocked in the same .b file? Yes, you will. You should be able to do that. It's just the two behavioral models. These are being synchronized by the same clock, right? So it's totally fine, right? It's totally fine. 2 always blocks in the same Verilog module, which is totally fine. Number 4: are you allowed to update a counter or AN at the same time in these blocks? Explain why. So what that means is you have different always blocks, right? Different always blocks. And in each always block, you have counts, the counter and AN over there at the same time. So for example, the first always block has a counter, and the second always block also has a counter as well. Are you allowed to do that in the same Verilog module? 2 always blocks, but if a counter in both. Why?
Because they're like being driven by different.
Yes, it's multiple drivers. Yeah. It's actually exactly the error you are seeing from Vivado. They are saying, oh, you have multiple drivers for the same signal line. That's the error message in Verilog, and that causes racing because there are being driven by the same clock, and it's gonna try to who is gonna win, right? This is eventually cause issues. So for AN, counter, and all these kind of things cannot be included in multiple always blocks, right? That wouldn't be functioning. So number five asks you to write an always positive edge clock, always block to swap AN0 and AN1 in AN10. And also increments counter by 1. Could you do that? So always if counter reaches counter max, right? You clear counter and you swap AN1, AN0. And otherwise, you increment counter by 1. Save it as you're not waiting for me. You guys can directly start writing up over there. So it's not a complete module, right? Just always block. So you can do always at begin if right? How do you swap it? Put ISB at the MSB spot and do a concatenation, curly bracket, right? Else, do what? So one trick here you guys should know. For count equals CNT max, because digital system is running so fast, there might be cases that CNT never reaches CNT max. You know, it's skipping numbers. That could be possible, right? Or it's just running so fast, it's running right at 100 megahertz, right? Even though it equals, because of something, hardware time delays or something else, it didn't trigger. It didn't trigger. And I just skipped that number where when it equals to that number, it didn't happen. And then it's gone. It will never satisfy this condition anymore. So how to avoid that issue to happen? So in the future, we probably don't want to do a counter equals counter max anymore, right? Whenever it allows, you should probably choose a different option over here. So what's the better option? If it skips counter max, I want to still catch counter max plus 1, right? You probably won't be able to see the difference because it's running so fast. I mean, when they're reaching 100 mega or 100 mega and 1, you are not telling the difference, but it's going to work, right? So if it skips counter max, we probably want to still catch it at counter max plus 1. So what you want to do here? Yes. So let's do this instead. It's a better option. Number 6. what is the logic expression for overflow bit, given that you have signal inputs, intermediate carryout, and output C2 and S2. Right? So I gave you two different options. You can just pick up the one we eventually want to use. Right, no brainer. That's the benefit of attending class. Ready? We'll do the answer. Okay. Number 7. What is the logic expression of the C2 final bit? It's also given. Do you make notes? Do you know that? The result for C2 final, right? C2 final. If you make notes, you should be able to know that answer as well. Number 8, write a 0 in parallel out module. Why we care about that is because for this lab, we have a fancier operation mode. Instead of just giving the numbers, we are using latches to latch the number in and then do the operation. So if you look at the structure, it has to be something like that. Let me show you really quick. It's okay since I'm an employee. Alright, the structure looks like this. FAs. So nothing to be changed over here. Okay. S2, S1. Here. Nope. C0, C1, C2, and these are S. Now opening this guy. Right. S, S2, S1, S0, and all the B's. And for A, we're not directly giving an A. Instead, we use a 0 in parallel out, the D flip-flop, so the D flip-flop. So that's D, right? That's D, and you have these guys to provide an A here, A. And you have 0 and 1 as a switch. As a D flip-flop, and these are Qs. These are Qs. And they are being synchronized by the same clock source. And that clock is not a 100 megahertz clock, definitely. It's going to be too fast. It's a clock. And that clock for the D flip-flop will be your hand, right? Your hand and a switch. So you put a switch over here. That's a switch, whatever switch you want to use. Let's don't abuse the first one. Let's use 15, okay, 15. And you got a clear output. Clear output. Let's see. So probably need 100 megahertz over here clock to synchronize the output to the input. So this is going to be a D bounce. It's going to be a D bounce module. Because the switch is a mechanical part, when you do it, it bounces back and forth and giving you a vibration. And you need a really clear rising edge over here to shift all the bits from D to here. Okay, so you have single bits. For example, these are the 3 bits you need: A0, A1, and A2. Okay. And you need one switch to provide a D. Whatever. Let's do 14, for example. Okay, how this works? So right hand is at switch 14, right? Left hand is switch 15. Okay? Depending on what the numbers you want to give to the A's, we start with A1 or A2 or A0. Which one you want to start first? There's only a switch, but you have 3 bits for A's. You have to do it one by one because it's a serial in, right? It's a serial communication. A0, right? A0 in first. So so right hand is switch 14. Left hand is switch 15, right? For example, A0 is 1, right? A0 is 1. Let's give a 101 for A. A0 is 1, right? Switch 14, give a 1, and then do what? Clock it in, right? So your left hand will be the switch 15, which is a clock. You do this, right? Give a rising edge, right? Give a rising edge. So is it going to be triggered at the falling edge because you are doing this, right? It comes back. Is the falling edge doing anything? No, because the Verilog code over here is only looking at the rising edge. So that's how you're writing here. The pass edge clock, always at the pass edge, right? The pass edge. So to this, where's A0 go? Where A0 goes? Here. Right? A0 goes here. But I need an A2 here instead, right? So that's not right. So we need to do it one more time. Then A0 will be latched at this line. It's being latched because of the latch. Keep in mind the latch. D flip-flop is going to be holding there. It's a memory. So A0 appears here. This becomes 1. And then you give a A1 as a data. You, switch 14, you put a 0. Yeah, switch it down. And then do a rising edge one more time manually. So A1 will be shifted in here and A0 will be shifted here. Because this is a serial, all of the D flip-flops are being connected serially, in series, and then D goes to Q, Q goes to D, and D goes to Q, right, in that kind of sequence. So eventually the A0 will be transferred here, and A1 will be transferred here. So you got A1, A0. Okay, and then you give A2 a 1, you switch 14 on, and then you do it one more time, do this. So A0 will be shifted here, and A1 shifted here, A2 shifted here. So you got all the A's available here. Okay, I only do it 3 times. If you do it one more time, what's going to happen? If you do it one more time, you just do it one more time. You only have 3 bits. After doing 1, 2, 3, right? You got all the A's available. And if you do it one more time, what's going to happen? Without changing this, the input becomes what? Without changing switch 14, given that number here, the input becomes what? You already have 101 here already sitting here, 101, and you don't change at switch 14, right? And then you do it one more time. What's going to happen? It becomes what? No, I mean all the numbers here becomes what? No, you're not changing this guy, right? After A2, you're not changing it.
1.
So A2 is what? 1. So 1 is not changing, right? So if you do it one more time, everything will be shifted to the right, and you're adding a 1 here. So it becomes what?
110.
110. Then you don't change it, keep doing this. What's going to happen? It'll be all ones, right? All ones. Right? This is what you can expect over there, right? Okay, so because you are not having any control of the output, so whenever you are doing this, you'll have intermediate values, and it's changing your result in real time. So you have to know when to stop and when to record the result, right? Since you know have 3 bits, you do it 3 times, and you know the result after the 3rd time will be the correct result. Then you log it. Make sense? So you see, this takes so long that we have to cover it in the lecture instead of just doing it in the lab. So I think we will start coding up the adder, and then on Thursday we'll cover the rest of it, and then we'll do the data storage units, the memories. Okay, so this is the structure of it. If you look at it in class, we probably won't be able to finish everything, but let's look at the serial in parallel out module. So this will be given to you guys, because again, you can always Google, right? So let's just go through this together. Serial in, parallel out, just by looking at the module, what do we need over here? Don't look at the debounce. Debounce is a different module here. Just looking at this module here. It's a serial in, it's really simple.
Clock.
It's in the clock, right? In the clock.
Serial in and yeah.
Serial in, just one bit, right?
Yeah, you need input and output.
And out, parallel out. All right. Yes. Let's see. Okay. It's gonna be something else, right? The top things are irrelevant. So we do module, serial in, parallel out, and you need the clock. You need the data in, right? Serial in, and you need the parallel out. Okay. So input will be clock and serial in. They are 1 bits. And output will be 3 bits, 220, and it's parallel. And we don't know if it should be a register or not for now, but we can just set it this way. If we need a register to shift it or to hold it a certain value in the OS block, we can always add a register type over there later. Okay, let's don't worry about that for now. So it's always at post edge of the clock, and we do begin. Let's indent it. Don't indent it. What can we do here? So it's basically as a behavioral modeling, right? We just describe the behavior. So the behavior is that we place, assuming that we can do PL. Let's do that first, and then we modify. Okay. So it's gonna be the PL. We don't care about the current value right now, but what we want is actually. Let's just write what we want. Don't think about the syntax for now, okay? Since we are spoiled, we just do whatever we want. Okay, this is the desired results, right? Desired behavior, right? What we want is just this. We place serial in as an MSB. We do, and then we place PL one. We shift. Wait. 3 bits, right? I think it's 1 0, right? 1 0. So the current PL, the PL. Wait, no. It's actually 2 to 1. You agree with that? Let me see. This is right. Yeah, this is right. Yeah. Because the LSB is shifted out. It's gone. So we got a 1 to 2. And then we shift every 1 to 2 to the right by 1 bit, and then we use the SI as an MSB. So every time we do this, it's keep being shifted to the right, and then we're done. This is actually everything we need. But however, the thing is, it doesn't like it this way because the port need to be a register type in order to be on the left-hand side of the procedural assignment in the OS block. So it doesn't like just a pure output being assigned like this. So we could do is we can add a temporary, right? A temporary, let's just go TMP, temporary, and it should be the same width as the PO. It's gonna be 220. It's a temporary register, and we modify the temporary one. Okay, we modify the temporary one. So it's all internal. So the register type temporary register, it's just a 3-bit D flip-flop right in front of the port, the output port. And these are just D flip-flops. You can modify, you can shift everything, you can modify, do the concatenation, do whatever you want. And eventually just assign the temporary output, you always assign them to the port, then you're done. So you could place the assignment outside of the always block. Okay. And the mod. Let's see if I'm missing anything. Okay, I think that's it. So the always block will be executed and be synchronized to the clock, the always block. However, it's a snapshot of the circuit by looking at the variable code, and this will be always true as well. So it's assigning this guy, the temporary, whatever the temporary register is being updated by whatever the value over here, it will be assigned immediately to the parallel output, so it'll be available at the port. Do we need a 4 bits or 3 bits over here? How many bits do we need for this temporary variable register? Do we need the 4 bits or 3 bits, and why? I think 3 bits will be enough, right? Yeah, there's no reason to have one more bit over there, because you combine these ones, eventually it's still just the 3 bits, right? You just have 3 registers, and you don't really need the LSB. It's being shifted out. It's gone. Yeah, I think that's it. So on Thursday, we'll cover the other modules like the debunks and adders and everything else, and also the data storage as well. So I'll let you guys turn in this one on Thursday, because we don't have the debunks yet. Alright, just keep it. You turn it on Thursday. So the lab this afternoon will be the traffic light control, right? So you can find the notes and video from the recorded video on my website. We covered that last week. All right, that's it for today.